Hello, in this video we're going to go over some subspaces associated to linear transformations and how we can actually find those subspaces and how they are related to dimensions of vector spaces. So here's a definition, and this is the main definition we're going to discuss today. Given a linear transformation L from V to W, the kernel of L is defined as the inverse image of 0, which means all of the elements that are mapped to 0. The image or range of L is all of the elements that are functional values of some vector. So this is the image you have seen before, and this one is the inverse image of a single point 0. So first theorem is these two are in fact subspaces of the corresponding vector space. So let L from V to W be a linear transformation, then kernel is a subspace of V and image is a subspace of W. So naturally we will use the subspace criterion. So we will use the subspace criterion. Okay, so in order to use the subspace criterion, we'll have to show that 0 is in the subspace and the subspace is closed under addition and scalar multiplication. So first 0 is in the subspace. In order to show that 0 is in kernel, we'll have to show L of 0 is 0. That's something that you can get pretty easily. In fact, this is something that I have done in one of the examples, but I'll show you pretty quickly. This means 0 is in fact in the kernel of L, and also 0 is in the image of L. So we showed that 0 is in both of them. Now we will take two vectors in kernel and we'll show that the sum is also in the kernel, and then we will also show that a kernel is closed under scalar multiplication. So let V and U and V be in the kernel of L. So by definition, L of U and L of W must be 0. This is by definition. Now if we take that and evaluate L of U plus V, we will get L of U by linearity. In fact, to be more specific, it's by additivity, and that's 0 plus 0, which is 0. And if you look at L of CU, that's CL of U by linearity. So here I'm using linearity. To be more specific, I'm using homogeneity for the second one, additivity for the first one. This is C times 0, which is 0. So these two tell us that U plus V and CU are both in kernel of L. So it means kernel of L is closed under addition and scalar multiplication. So we'll do the same thing for the image. So we take two things in the image. So suppose W1 and W2 are in the image of L and I have a scalar. So that means W1 is L of V1 and W2 is L of V2 for some V1 and V2. That's by definition of image. And what does that mean? It means if I add them, W1 plus W2, I will get L of V1 plus L of V2, which is L of V1 plus V2. That's by additivity, which of course is in the image by definition of image. So let me specify in every step what I used. Here I used the linearity of V, L, and here I'm using the definition of image. And finally, CW1 is CL of V1, which is L of CV1, and this is by linearity. So here I'm using linearity, which means CW1 is in the image because of the definition. So this is by definition of the image. Image is just L of elements in the domain by definition of image of L. So therefore, both of these sets are closed under addition and scalar multiplication. Therefore, they are both subspaces, and also 0 was in both of them. Thus, kernel of L is a subspace of V, and image of L is a subspace of W. Okay, so that completes the proof of this one. Let me just be a little bit clear about the differences between the zeros that I used here. So if I go back and look at these zeros, I have 3 different zeros in fact here. The first 0, which is the input of L, this one is in fact in V. So usually I would denote that by V sub 0 sub V. That means it's the 0 of the vector space V. That could be different from the 0 of vector space W, because V could be in R3 and W could be in R5. So those are not the same thing. This 0 is the same 0. It's 0 sub V. This 0 is a scalar. This 0 is also a scalar. This one is 0 sub V. But this one is actually 0 sub W. What does that mean? It means it is in the image. It is in the range, not in the domain. So those are different zeros. Now, this one is in V. This one is in W. The first 0 is the input that is in the kernel. The second 0 is the output that is in the kernel. This 0 right here is in W. So you see there's actually differences here. I believe the rest of the zeros are all in W. Okay, so just be careful about that. So let's do an example on kernel and image. How do we find kernel and image of linear transformations from Rn to Rm? So by this example, you should be able to tell how to find kernel and image. So I'm giving you this linear transformation, and I want to show that I want to find the kernel and image of this linear transformation. Okay, so first you will have to see that this transformation is in fact linear. Otherwise, we can't really talk about kernel and image. But that one is not very difficult to see if you look at this one and think of that as a matrix multiplication. So this would have to be a 2 by 3 matrix times xyz. 1 to 1. If you multiply xyz by 1 to 1, you'll get x plus 2y plus z. And then 2 negative 1 negative 1 gives you 2x minus y minus z. So this is the same matrix. Now by a theorem, any matrix multiplication gives us a linear transformation. So A is in fact linear. Okay, now that we know this is linear, we can find its kernel and its image. So how do we find the kernel? So kernel of L is all of the elements that are mapped to 0. It's the set of all x, y, z such that L of x, y, z is the 0 vector. What does that mean? It means we're trying to solve a system of equations, which is to say we're trying to solve 1 to 1. The augmented matrix would be this. So this is the augmented matrix. We are trying to solve the system of equation that this is the augmented matrix. So we're going to ignore, as usual, when you have homogeneous systems, we're going to ignore the last column, and we're going to row reduce this. So we will do R2 minus 2R1. That would give us 1 to 1. Again, I'm going to ignore the last column. And this would be 0. I'm multiplying the first row by negative 2, adding to the second row. Negative 4, that's negative 5. Negative 2, that's negative 3. And I'm trying to solve this one. I'm trying to find the kernel, which means I'm trying to find all the solutions. So I'm going to multiply the second row by 2/5 and add it to the first row. That would leave the second row intact. It would make this one 0. And this one becomes negative 1 over 5, I believe. Yes, okay. So this is what I get, which means what I'm going to end up getting is x minus 1/5 z equals 0 and negative 5y minus 3z equals 0. So this system gives you all the solutions to the ax equals 0, axyz equals 0, or L of xyz equals 0. This gives you x equals 1/5 z and y equals -3/5 z. And of course, these are all if and only if, which means xyz is in the kernel if and only if xyz is equal to 1/5 z, -3/5 z, and then z. And that's z times 1/5, -3/5, and 1. So what does that tell us about the kernel? It means kernel is all the multiples of that vector, and another way of saying that would be the span of that vector. So kernel of L is the span of this vector 1/5, -3/5, 1. So that is the kernel. You could write it down as a row vector, or you could write it down as a column vector. I typically keep these as columns because of the matrix multiplication, that it works better when you think of them as columns. Now, in order to find the image, this is what we need to find. So image of L would be all of the L of V, where V comes from the domain. What does that mean? It means we'll have to look at, so let's write down what this means. This is L of xyz. This is the same as, so if you write it down, you get x times, so I'm going to just write down the formula first, x plus 2y plus z. So let me just write it down first. X plus 2y plus z, comma, and the second one was 2x minus y minus z. If we break this up, we get 1, 2, y times 2, -1, and z times 1, -1. In other words, image is all the linear combinations of these three vectors. So what does that mean? If you look at the matrix that we looked at, the augmented matrix, these columns are exactly the coefficients of x, y, z. Not surprisingly, because that's how matrix multiplication works. So in other words, image of L is exactly span of these three vectors. Span of 1, 2, 2, -1, and 1, -1. And this, if you recall, this is called the column space of A, where A is exactly the matrix that we started with. It's the 1, 2, 2, -1, 1, -1. Now, how do we find column space of a matrix? What we did was we found the reduced echelon form, or just any echelon form, and then that the number of pivots told us the dimension, and then we could go back and look at the original matrix, and those would give you a basis. So now we have two pivots here. If we go back and look at the matrix that we found, we have two pivot entries, this one and this one. So that tells us that the dimension of the column space, so the dimension of the column space of A is 2, but the column space of A is inside R2. So every subspace of R2 that is of dimension 2 must be the entire space. So column space of A must be R2, and this was a theorem that we proved earlier in a previous video. So that tells us that image of L is R2. So image of L is the entire R2, and kernel is a one-dimensional subspace. So this is interesting. So we got that the kernel is one-dimensional subspace, and the image is a two-dimensional subspace. The domain, if you recall, was a three-dimensional space. So it was R3. So part of R3, if you look at the domain, it was a three-dimensional space. So what happened here was the kernel was some line, and the image was the entire R2. And this is actually something that always happens, and we'll talk about that in a later theorem today in this video. Okay, so next theorem. This theorem tells us that a linear transformation is one-to-one if and only if the kernel contains only the zero vector. So if kernel of L contains only the zero vector, then the linear transformation is one-to-one, and vice versa. If L is one-to-one, then the dimension of the image and the dimension of the domain are the same. In other words, it preserves everything. So it kind of makes sense. So it doesn't collapse anything to zero. It means it preserves the dimension. So we will prove this one. Not very difficult to prove. So the first part is if and only if. So we will have to do two things here. So suppose kernel of L just contains the origin. We will have to show that it is one-to-one. So suppose L of x equals L of y for some x and y in the domain. We are going to use linearity here. So if we bring everything to the same side, we will get this equals 0, which means L of x minus y is 0. Now, this tells us that x minus y, by definition, is in the kernel. But kernel contains only one single point. That means x minus y is 0, and that means x equals y. So what we showed was, if L of x is equal to L of y, then x is equal to y. Therefore, L is one-to-one. That's exactly the definition of one-to-one. If L of x equals L of y, then x and y are the same. So now we're going to do the backward direction. So we're going to assume that the kernel is, we're going to assume that L is one-to-one, and we're going to show the kernel is 0. So suppose L is one-to-one. We would like to show that the kernel contains only the zero vector. So first of all, since L is linear, 0, L of 0 is 0, which means 0 is in the kernel. So if I want to show that, so the objective is this. The objective is to show kernel of L contains only the origin. We know that 0 is in all kernels because L of 0 is 0. That's what we just did. Now, assume that you have x in the kernel, and we'll have to show it's just 0. So this means L of x is 0 by definition of kernel, but 0 is L of 0. That's again because it's linear. So that implies since L is one-to-one, x must be 0. So if something is in the kernel, it must be 0. And 0 is in the kernel, therefore kernel is just 0. So therefore, kernel of L contains only the vector 0. Okay, so we showed that L is one-to-one if and only if the kernel contains only the origin. Next part is assume L is one-to-one and then show that the image and the domain have the same dimension. So now suppose L is one-to-one, and we'll have to show that the domain and image have the same dimension. So let V1 through Vn be a basis for V. What I need to show is that image also has a basis of size n. So this basically means that dimension of L is n. Now, the most natural thing to do would be to take the image of these elements and then show that L of V1 through L of Vn is a basis for the image. So we will show L of V1 through L of Vn. These form a basis for the image. In order to show it's a basis for the image, we'll have to show two things. First, it is linearly independent. They are linearly independent. And second, they also span. So linear independence. So suppose C1 L of V1 all the way to Cn L of Vn is 0. I'm going to use linearity to write it down as L of C1 V1 plus Cn Vn equals 0. But I know that L is 1 to 1. So if L is 1 to 1, that means, so 1 to 1ness tells us C1 V1 all the way to Cn Vn must be 0. And what does that mean? I know V1 through Vn is a basis, so they are linearly independent. That means C1 and Cn are all 0. So we started from a linear combination of L of V1 through L of Vn, that is 0, and we showed that all the coefficients must be 0. Therefore, they must be linearly independent. So L of V1 through L of Vn are in fact linearly independent. Okay, now I will have to show that in fact these not only are linearly independent, but they are also spanning. So let's just start from something in the image. So suppose W is something in the image of L. Okay, so if something is in the image, it means it must be L of something. So by definition of image of L, W must be L of some V. For some V in V. Okay, so what does that tell us? It tells us that I can write down W as L of V, but then I can write down V as a linear combination of V1 through Vn, because V1 through Vn span V. So let me write it down in the next line. So since V1 through Vn span V, because they are a basis, so every basis is also spanning. C1 V1 plus Cn Vn is equal to V for some scalars C1 through Cn. Now I will just take L of both sides. So L of V becomes L of C1 V1 plus Cn Vn. And all you have to do is now to take the C1 out and Cn also out. Just use linearity. So this means W is in fact a linear combination of L of Vi's. So I'll just use the sigma notation here. So this means L of V1 through L of Vn span image of L. Therefore, we found a basis of size n for image of L. And this means dimension of image of L is the same as n. So we showed dimension of image is the same as dimension of the domain. And that is exactly what we wanted to show. Just remember that this is only going to work when L is 1 to 1. Now, here's the next theorem. This is also a really useful theorem, and then we'll finish it up with the last theorem. Suppose L from Rn to Rm is a linear transformation whose matrix in standard basis is A. Then there's a close relation between the column space of A and the image of L. So let's write it down. So let's assume that columns of A are A1 through AN. So remember that if you have a linear transformation from Rn to Rm, the matrix would be m by n. That's how matrix multiplication works. Now let's compare image of L with column space of A. So image of L means all of the vectors of this form, L of V. L of V is A times X. So let's start with some X inside Rn, x1 through xn being Rn. If you look at L of x, we get this, and that gives us a1 through an multiplied by a column x1 through xn. And if you multiply that, you get x1 a1 all the way to xn an. So image is exactly set of these, but these are just linear combinations of columns of A. So image of L is exactly the set of all x1 a1 plus xn an, such that x1 through xn are real. That's by definition. All I did, I substituted L of x with that. But that is exactly the definition of the column space. This is exactly the definition of column space. So image of L is just the column space of A. Let's look at the second part of this. And just to be clear, these are exactly equal sets. So I didn't actually need to show one is a subset of the other one is a subset of this one, because really what I did was I wrote down the definition of image and I substituted L of x by something that was exactly equal. Okay, and since this works for every x1 through xn, those are identical sets. Next thing I need to do is to show that the kernel is in fact row space perp. And this perp is with the dot product. So in order to show these two are the same, I will have to show every element in the kernel is in the row space perp, and every element in the row space perp is in the kernel. So let's write down what that means. So if you look at L of x, again we know this is A times x. So what is the definition of this? The definition of kernel, it is that this is exactly 0. So x in the kernel of L implies, and we can also like do something that is if and only if. So let's write down A. Let's write it down this way. So this is in the kernel if and only if AX is 0. If you make sure that everything that you're writing down is reversible, then you can show both inclusions at the same time. Okay, so we're going to start from x in the kernel. That is equivalent to AX being 0. That's just because by definition, this is equivalent to, maybe I'll write down one more step here. This is equivalent to saying L of x is 0, and just replacing L of x by AX, we get AX is 0. Now let's understand this AX 0. So what does this mean? So let's suppose that A is equal to B1 all the way to Bm. These are rows of A, is the jth row of A. Okay, so let's write this down. So this is the same as B1 all the way to Bm times x equals 0. What does this mean? If you write down what matrix multiplication gives you, it gives you B1 dotted with x all the way to Bm dotted with x. That is equal to 0. And again, this is if and only if. This is if and only if B1 dotted with x all the way to Bm dotted with x is equal to 0. So what we showed is, if something is in the kernel, then the dot product of that and all the rows of A are 0. And if the dot product of x with rows of A is 0, then it's in the kernel. But that doesn't exactly mean that it's in the row space perp, because row space is the set of all linear combinations. So there's a connection here that needs to be made. But we're going to use this and make that connection to complete the proof. Okay, so suppose x is in the kernel. So that tells us, by what we showed above, let's call this a star. So that tells us B1 dotted with x is 0. And so is B2 dotted with x and Bm dotted with x. All of these are 0. that doesn't exactly mean that X must be in row space perp, because what we just showed is that it's orthogonal to all the rows. We haven't shown it's orthogonal to everything in the row space. If V is in the row space of A, then we can write down V as a linear combination of these rows, j equals 1 to m. And that means if I do V dotted with X, then I will get sum of Cj Bj dotted with X. And if we use linearity, we can show that this is equal to Cj Bj dotted with X by linearity. And this is of course 0 because all of these are 0. So what we showed is that X is orthogonal to everything in the row space, and that tells us that X is in fact in the perpendicular complement of row space. So if X is in the kernel, we just showed that it's in row space perp. Now, if X is in the orthogonal complement of row space, then I guess I forgot A in front of row space. So let me write it down completely. Okay, so if that's the case, then by definition, X is orthogonal to every row of A for every j1 to m. And that by star means X must be in the kernel, because we just showed that being in the kernel and being orthogonal to all the rows is equivalent. Those two things are equivalent. What does this mean? It means these two sets are the same. Therefore, kernel of A is in fact the same as, I guess I said kernel of L, not A. Kernel of L is in fact perpendicular complement of the orthogonal complement of the row space. Okay, so that proves the second part of this theorem. The last part tells us that dimension of the kernel and dimension of image add up to L. So what does that mean? It means if you look at the kernel is the part that disappears in the linear transformation. It all goes to 0. That part completely disappears. The rest of it is going to remain intact, basically the rest of the dimension. So if the dimension of kernel is 5 and dimension of the domain is 7, then you're going to have a dimension 2 as the image. Okay, so let's prove this one. But in fact, I'm going to prove that in the next theorem, because this is actually a more general theorem. So I'm going to do that for every vector space. So I'm going to skip this theorem, because in fact I'm going to prove that in a more general case here. This is called Rank-Nullity Theorem. So let V and W be vector spaces. L from V to W be a linear transformation, then dimension of the kernel plus dimension of image is dimension of V. That's exactly what I have here. Dimension of kernel plus dimension of image is equal to n. N is the dimension of the domain. Dimension of Rn is n. So if I prove this theorem, then the previous one would have been will be proved as well. Okay, so let's prove this one. So I'm going to assume that dimension of k, kernel of L, is perhaps k. So let dimension of kernel of L be k and dimension of V be n. Remember that kernel of L is inside V, so it's a subspace of V. We can choose a basis for dimension of kernel of L and then extend it to a basis of V. We have done this before, that if you start from linearly independent vectors, then you can extend it to a basis of the entire space. So suppose V1 through Vk form a basis for the kernel of L, and V1 through vk all the way to vn form a basis for v. So how do we know this one? This was by an exercise. I believe this was an exercise. Every linearly independent set can be extended to a basis. So what does that mean? It means if I start from v1 through vk, then I can extend it to a basis of the entire space. Now what I'm going to do is I'm going to show the rest of them are going to give me a basis for the image. So we will show, if I look at L of vk plus 1 all the way to L of vn, this form a basis for the image of L. And if I do that, then I'm basically done, because that means the dimension of the image would be n minus k, and dimension of kernel is k, so the total becomes n. In order to show it's a basis, we'll have to show it's linearly independent, and they also span the image of L. So let's just start from linear independence. So in order to show they are linearly independent, we'll start from a linear combination that is 0, and then we'll show that the coefficients must be 0. So suppose I'm going to use ck plus 1 because it's the coefficient of L of vk plus 1, even though it doesn't really matter. Suppose this linear combination is 0 for some scalars ck plus 1 all the way to cn. Now I will use linearity and see what we get. So by linearity, ck plus 1, L of ck plus 1 vk plus 1 all the way to cn vn becomes 0. But this is exactly the definition of kernel. It means this guy is in the kernel. So ck plus 1 vk plus 1 added to cn vn is in the kernel of L. But what does that mean? It means ck plus 1 vk plus 1 all the way to cn vn is a linear combination of v1 through vk. Why? Because let me first specify what these ci's are. For some constants, scalars, yes, c1 through ck in R. So why does that hold? The reason is v1 through vk are generating. So since v1 through vk span the kernel of L. Now if we bring everything to the same side, we're going to get c1 v1 all the way to ck vk minus ck plus 1 vk plus 1 minus cn vn is 0. But we know that v1 through vn are linearly independent. So that means c1 ck ck plus 1, in fact negative of those, but these are all 0 since v1 through vn are linearly independent. Okay, so that means the coefficients ck plus 1 through cn are also 0. So what does that mean? That means that L of ck plus 1, L of vk plus 1 all the way to L of vn, these are linearly independent because we started from a linear combination equals 0, and we ended up that the coefficients must all be 0. So now we will have to show they are also generating. So we'll start from something in the image. So let W be in the image of L What does it mean that it is in the image? It means W is equal to L of V for some V in V. So now from here, we know that V must be a linear combination of V1 through Vn. So V is equal to C1 V1 all the way to Cn Vn for some C1 through Cn in R since V1 through Vn form a basis for V. Okay, so because they form a basis for V, we can write down V as a linear combination of those. Now let's evaluate W. So W is L of V, which is L of C1 V1 all the way to Cn Vn. The first portion, if you use linearity, you'll see that it's going to be 0 because L of V1 all the way to L of Vk, they're all 0 because V1 through Vk are in the kernel. The rest of them may not be 0. So you'll get Cn L of Vn. So these are all 0 because V1 through Vk are in the kernel. So this would be Ck plus 1 L of Vk plus 1 all the way to Cn L of Vn. So we just showed that W is a linear combination of L of Vk plus 1 through L of Vn. Thus, L of Vk plus 1 through L of Vn span image of L. Therefore, they have to be a basis. Therefore, L of Vk plus 1 all the way to L of Vn form a basis for the image, for image of L, which means dimension of the image of L is exactly n minus k. But dimension of kernel of L was k because V1 through Vk was a basis for the kernel. So what does that mean? It means if you add them up, dimension of kernel of L and dimension of image of L, you end up with n, which is dimension of the domain. And that brings me to the end of this video. So I will see you in the next video.